All right, we're back for day 23 of Advent of Code. Here we go. This looks like a graph. Find all sets of 3 interconnected computers. How many contain at least one computer with a name that starts with T? Okay. Default dict set. Let's do. Okay, get this. And then, what's the size of this? That's kind of big to do a cubic thing. Maybe it's fine. We only want unique triplets. And then now we can find the triplets by doing g of A intersect g of B. And that gives us all triplets. This is a possible set of C's for every possible candidate C. It starts with a T. Not the right answer. What did I do wrong? Okay, connection between every 2 computers. I should think of this. Sets of 3 computers, each computer set is connected to the other 2 computers. 12 such sets of 3 interconnected computers. At least one computer starts with. Oops. These are the edges. 62 seems high. Oh. Let's assert that C is greater than if C greater than A and C greater than B. 20. That seems wrong. ABC. Putting duplicates. I don't see dupes. Why do I not see dupes? This one doesn't appear. Each computer is connected to the other 2 computers. These are adjacencies. They're bidirectional. What did I do wrong? What? Where did my thing go? There it is. I could just throw them all in a set, like order them, but I don't think I have dupes here. I just think that KHCOTC does not appear in this one. KHTC, and then KHC appears in both A and B's sets. Oh, A and B need to appear in each other's sets. Ah, shoot. Now we get 7. Okay, cool. This looks good now. Oh, I lost so much time to that. Rank 245. Okay. Largest set of computers that are all connected to each other. Okay. Largest set that is all connected to each other. I wonder if there's like good heuristic-y ways to do this. Let's count the degree of each node first. Everything's connected to exactly 13. Is that right? I don't know, but we'll find out. Yes, everything's connected to exactly 13. That's a little bit interesting. I guess that means that it's going to be a set of exactly size 13. We can't brute force that necessarily. Let's try the following. For each node, let's see. Oh, well, yeah, it might be the case that it's just almost completely disconnected. If there's a bunch of like size 13 globs, probably not. But this graph definitely has some structure that makes this unique. I'm not sure exactly what to get at here, like what kinds of things to check about the graph. Or if I should just throw this in a network X and find maximum. Let me see if people have been solving. If people have been solving, then it's network X. Oh, people already solved. It's already full on part 2. Oh yeah, it's full of LLMs. Okay. Man, that's sad. But that implies to me that it might just be something silly, like we look up network X largest click, max click. Oh yeah, what do you know? Well, I guess we'll just do that. What about algorithm it uses? No matter. I need to remember the network X syntax, but what? Oh. I forgot the X here. Yeah. Okay, yeah, so this is just implementation now. Interesting. I wonder if the LLMs got access to network X. Like if people put that in their prompts or something. G.add edge. I guess they must have to do some of the earlier problems. Maybe not, but this is it's not a directed graph, so I think this should just be fine. So we think we just do this, and then we do approximation. Do I need to import this? I thought the alias might work there. Does that work? No, it doesn't. Oh, okay, thank you. Then approximation max click on G. Oh, it's pretty slow. I mean, the problem is NP hard in general. Is there something more clever for this? If I know the size of the click, does that help? Probably not. Oh, there it is. Okay, it just takes a second, but it does spit it out. Then join together with commas. Is that right? Yep. That is not a comma. Well, now I gotta copy it into a thing, into a variable. There's our answer. No? Oh no. Surprising. This is of size 12. I guess we'll try the sample input. Oh, that's not right, is it? You know, just in case I'm going to add the other edge, I don't think it should matter. No, because it's an undirected graph. It means a direct connection, right? Surely. Can I index it like this? Oh, I can. CO is connected to these. TA, DE, KA. TA, CO, DE. Yeah, I'm thinking that this is just not working. Approximation max click. Oh, it is an approximation. Well, is there a way to find clicks? Maximal click. I guess we could just try iterating the clicks, but find clicks of G. Doesn't like this. I thought that's how you make an empty tuple. Okay, well, this one finds it instantly. How about now? Oh yeah, it finds it instantly. Weird. I guess the approximation algorithm that it uses is pretty bad. Rank 372. Okay. Yeah, so that was a little disappointing. That it ended up just being... So this is a pretty standard problem in graph theory, or like graph algorithms. So I guess now I'll just explain the whole question and the approach. At least the approach in my case was just use a library, but I'll still explain it a little bit. So we're given this graph, this undirected graph. We have edges between computers in the graph. And the first thing we're asked is find every like triplet that is connected. So find all triangles in this graph. And then for each of these, like how many triangles have at least one computer that starts with the letter T? Yeah, and for this, the graph is 500 nodes, so it's maybe it's actually not too large to like brute force if you do it cleverly. Yeah, I think actually if I'd done it like this, so first you pick the first node, and then you pick the next node from the adjacencies of this first node, and then you pick the third node from the adjacencies of this node, and then if this is not in the adjacencies of the first node, does this work with my new graph, by the way? Let's check. Yeah, that seems to work. And if the third, I think if you do it this way, it should just be fine. Otherwise, if doing the check here instead of earlier is a little wasteful, but this might work. What was my answer? It was not this because I forgot to do let's like assert the invariant. So you need to do something to make sure that when you're iterating through triangles that you don't double or triple count triangles. One easy way to do that is because the nodes are strings, is you just only consider a triangle if the first node you've considered is less than the second node is less than the third node. So I will just check that right now. Yeah, and that just works. Yeah, so you can straightforwardly brute force this. The thing you probably can't do, I'm guessing, is you probably don't want to do like for A and G, for B and G, for C and G, and then check everything here. Because if you do this, you end up considering a lot of possible edges that like would never possibly, or like a lot of triplets that would never possibly have been triangles, because there just aren't any edges between these nodes. And in actual fact, there are 500 nodes in this graph, but the degree of each node is 13. So there's actually, like, it's a pretty sparse graph in some sense. And by doing this would be like very wasteful. I assume this doesn't work, but I'm actually just going to try it now because I'm curious how. To be clear, by doesn't work, I mean, I assume it's not efficient enough. But we could just try it. No harm in doing that. I wonder what the best way to write this is. A and G of B, and B and A and G of C, and B and G of C. I think that's fine. Yeah, this is pretty slow. Yeah, it might get a little bit better if you do some of these checks like further up here, but then you're getting pretty close to this approach where you're only iterating through the adjacencies. But yeah, this is the thing I first thought of and I didn't do. The like brute force with a tiny bit of optimization works just fine. There we go. And yeah, so that's part one. Part two says now, instead of finding the triangle, or instead of finding triangles, you want to find the largest set of computers that all have edges connecting each other. And this is a pretty well-known problem known as the max click problem in graph theory, or I guess just the click problem, which is identifying like fully connected subcomponents of the graph, or also called clicks. And yeah, it's generally NP hard if you want to find the maximum size click in a graph. But there exists like ways of approximating it. And I guess, so when I saw this, my first thought was there's either some structure in the graph that makes it easier, or you just throw some tool at it. Some tool being like network X. And I ended up throwing network X at it and it worked fine, with some difficulties. Network X exposes a max click, which is an approximation algorithm. I missed this as it finds the O of V. I assume this APX stands for approximation. But yeah, I didn't really realize at first that this was, I saw approximation and heuristics and I thought, oh, heuristics, maybe it's like trying some heuristic to find it quickly. But no, it actually does not find, in fact, the maximum click. It finds an approximation of the max click, I believe. And it did not actually find the max click for me. It found something that was one less than the max click, which is pretty sad. In actual fact, this problem does have a lot of structure to it. Here, let me actually just do, let's make the problem, sorry, I'm just going to reorganize my code a little bit to make it clean and outputting both things. Cool, first answer, yeah, I don't need the last print C. Cool. Yeah, so this didn't find the max click, but turns out there's actually a find clicks function in network X that returns all maximal clicks. And the difference between a maximal click and a maximum click is a maximal click is a click that cannot be locally improved anymore. So you cannot add any nodes to it and keep it as a click. This is different from the maximum click, which is like the largest click overall in the graph. So if you have like a graph that has, I don't know, if it has like a triangle here, and then it also has a click of size 4. So click of size 3, click of size 4, and maybe they're connected. Like let's make the whole graph connected. This is a maximal click. This is also maximal click, but only this is the maximum click, this one. And this is maximal because you can't add any other nodes in the graph right now to this and make the click larger. But yeah, and the idea is that this will return all maximal clicks, and there could be very, very many maximal clicks. My vibe is that it's exponentially many, but I'm not actually sure. I think it said something about this as well. Yeah, it can be exponentially many. So, and this function doesn't actually do that, but anyways. But it turns out, I think probably because of the structure of this, where the degree of every vertex is 13, it's the case that there aren't that many maximum clicks maximal clicks is my guess. But yeah, so just doing this function, like finding all the maximal clicks and then taking the largest of those worked just fine. And that was how I ended up solving it. I don't actually know how it does this. I would guess it's some variant of like pick a node and then greedily add more nodes to it and then like recursively backtrack. And this is actually a thing I thought about writing before I decided to punt to NetworkX, figuring that NetworkX probably already had it written, which it did. But yeah, that is the idea behind day 23. And I will see you tomorrow.